Yeah, Assalamualaikum and good morning. Welcome back, everyone, to our online class. So I hope you are doing in the best health and keep on staying safe in your place. Uh, so today we will continue discussing about the transducer and application. Last time we stopped at our discussion at thermocouple. Okay. So today we're going to look at the what is called as resistor temperature detector, and basically a resistor temperature detector or an RTD is an alternative to thermocouple in many application, industrial application especially due to their higher accuracy and stability. Okay. Uh, in terms of size, they are relatively smaller as compared to thermocouple. But a few things that we need to know, like RTD is a passive transducer. Okay. So that's a few point that we have to know. RTD is a passive transducer, type of passive transducer. Passive. Okay, so what what it means by passive? So it does not generate its own EMF signal. Okay, so in electric and electronic instrumentation, okay, usually the signal that we want to measure is either voltage or current. So this sensor, the relationship between the temperature, okay, is based on the metal resistance increasing with temperature. Okay. So it is a temperature sensor that is used to measure temperature by associating the resistance of the RTD element with temperature. Okay. So we have temperature, okay, associated with the resistance change. Okay, I mean the change, rise or change in temperature associated to the change in resistance of the device. So then to measure to couple the output with our electronic system, okay, so we have to measure the uh, resistance or the or find the relationship of the resistance with the change of EMF voltage. So that we can be done by um, configuring the RTD, okay, or connecting it in series with the fixed resistor in a simple circuit. Okay, okay, we give an external power supply, okay, to the circuit, and then we measure the output across the RTD. So then we can get the good EMF relationship. So this is a passive transducer, meaning that it does not uh, generate its own uh, voltage or output voltage. Okay. So the so best the in principle, so into the construction, and RTD basically is a piece of metal, okay, piece of metal wire, okay, twisted into coil, and the coil is packed together, close together. Okay. So as you can see from this figure, so the coil is packed together and put into a casing. Where before you put the casing, we uh, cover the platinum, okay, the platinum wire coil with ceramic material like ceramic. Okay, so we will see why we do that. Then the common metal that is used as a RTD, okay, can be either platinum. It can be any practical metal like platinum and nickel. Okay. But platinum, okay, one of the common metal is used to make to construct an RTD. For platinum, it is used because it has a high repeatability, means that we can have a consistent output. Okay, when we repeat the measurement, okay, every day, every month, or every a certain period of time. As I said, we can get a consistent output with a consistent in, temperature or, or condition. Okay, and also in platinum is quite sensitive. Okay, and other advantage using platinum like it is inert to foreign chemical, inert to meaning that platinum when it is exposed, okay, to certain chemical, uh, like in many industrial application, the situation can be harsh, sometimes can be corrosive. Okay, sometimes the application is basically an open space to the environment, the outside. They're exposed to the natural element like the heat during the day, cool and humidity, dew in the morning. So platinum is quite inert. It does not easily oxidize. It does not easily corroded. Okay, like common metal like zinc. Okay. Uh, that's why we see platinum being made into jewelry. Okay. So they are very inert. It can stay, if you make it into jewelry, it can stay shining for quite a long time. Okay, but with the drawback for platinum is very expensive in terms of the price. Okay. In terms of the price, platinum is very expensive. If I'm not mistaken, it's much more expensive than gold. But it doesn't have any, but the reselling price is lower as compared to gold when you think about jewelry. Right, but and other common metal being used is nickel. Okay. And nickel, although it's not quite repeatable and sensitive, so maybe so the that when we use it for a long period of time, okay, we will see some zero drift. Okay, come into the measurement. Okay, coming to the measurement. Okay, uh, and it is not quite sensitive, meaning that the output or the response is less uh, as compared to platinum when it is exposed to the same temperature change. Okay. But the uh, the reason why nickel is popular or available, one of the reasons is they are less expensive as compared to platinum. Okay. But if you think about the long term, okay, if we use platinum, of course, the starting cost is quite expensive. But in the long run, uh, the invest we can get back our investment. So, in my opinion, it's better to use a platinum RTV device as compared to use a nickel RTV device. Okay. And the relationship of the RTV is given by this formula. RT is the change of resistance. RT is the change of resistance, and RTO, okay, RTO is the reference resistance. Okay, reference resistance. So when this device or RTD is constructed, we have to consider the reference resistance. So this reference resistance is fixed at certain temperature. Okay, like for example at 0 degrees Celsius or or at 25 degrees Celsius, which is the common room temperature. Okay, okay. Multiply with 1 or plus alpha delta T. Alpha is the temperature coefficient of the resistivity. So this is the constant of the material. Okay. Constant of the temperature coefficient of the resistivity of the material. So platinum have a different alpha, nickel has a different alpha. Okay, and delta T is the temperature change. Temperature change means that what that, delta T is the current temperature T2, the current or the measured temperature minus the reference temperature, which is TO. TO is the reference temperature. So it depends on the reference temperature that is used. Okay, it can be at 0 degrees Celsius or 25 degrees Celsius. Okay, we will look into that example later. Okay, so as I explained, RTD is basically a piece of wire. Okay, twist or bend into made into a coil. Okay, and then the coil is packed close together. So it's just basically a piece of wire. Okay. Uh, so it won't to form a coil. Okay. So the reason why it is formed into a coil because if we leave it as a long wire, so we will take more space. Okay. So when we pack it, so we package into we pack in we can package it into a smaller size. Okay, smaller size. And also the reason why we turn into a coil, smaller, we have a smaller total dimension because heat, okay, heat, it takes time to distribute. Okay, heat is this if you think of heat distribution. Okay, um, other parameter like light, it can travel very fast. So when we measure the light intensity from the source, So we can do the measurement immediately, but for temperature, when we expose the RTD, okay, to an environment, or we contact, okay, the RTD to an object that we want to measure the temperature, so we will not get the exact temperature immediately. So the heat from the source, okay, will take some time to transfer. Okay, so an RTD, okay, so it has cover casing. Yes, it has casing. So the casing itself, it has some heat resistant behavior, but basically it actually a good conductor. But of course, any material it will have heat resistant behavior. So it's just a matter of whether the heat resistant behavior is small or big. But so the heat will take some time to transfer, okay, from the source to the element. Okay, so the other element is in the middle. Okay, and so so the we cannot just use the element in a raw form, or in its original form, because the wire is not that strong. It can easily be bended, or can be easily be exposed to slight force. Okay, so we need to give a stronger protection, okay, using a cover, okay, what is called as the protective tube. Okay. And also in the core, so we cover, basically we put a cast the RTD element into ceramic support. Okay. So it is put into a ceramic. So the purpose, there are two purposes why we use ceramic. Okay, first to increase the transfer of heat from the source to the RTD element, and secondly is to protect, okay, to protect the RTD element from vibration. Okay. So this is the purpose of the ceramic material. Okay. So if this RTD is used in higher temperature, or if there is a vibration in the application, a lot of vibration, so the ceramic material will protect, okay, the RTD element from the extreme temperature and also from the vibration. So the ceramic support acts like a damper, so it will absorb most of the vibration, okay, and then it's transfer the vibration away from the RTD element. So that's why there is a ceramic support surrounding the RTD material. Okay, and as you can see from the figure on the top, so there's a RTD. It looks like a small semiconductor device, has a two terminal. So these two terminal, yeah. So the RTD has no polarity. Okay, polarity. So doesn't matter if you connect this as a first and the second point, or vice versa. It doesn't matter. It's no polarity. And also, some RTD is made into a SMD device, like we have shown in the bottom right picture. Okay, so the RTD can be mounted on a PCB, so maybe it can be used uh, or it can be integrated to a printed a small printed circuit board to measure temperature on a certain environment. Okay. So these are the characteristics. So characteristic is very important for any transducer. So if you run any, okay, if you run any transducer application, so you need to know the characteristic of the transducer. Okay, the basically the sensitivity is one of the main characteristic of the RTD, where the sensitivity is determined by the value of the temperature coefficient alpha. Okay? So alpha is depend on the material type of the material, and also RTD has a linear sensitivity. A linear means that uh, in general, the temperature, so the resistance change increase linearly with the temperature, change of temperature. Okay. Uh, for example, for platinum, the sensitivity is 0.004 per degree Celsius, and for nickel is 0.005. But I think it should be other way around. Yeah, platinum should have a higher sensitivity as compared to nickel. But by the way, the sensitivity is around um, 10 to the power of negative 3 per degree Celsius. Okay? So that's the range of sensitivity for RTD. Okay, so the RTD, the response time, it has quite a, I mean, the response time is not that great. Okay, the can be between 0.5 to 5 seconds. So in the point of instrumentation, so this is quite. I mean, the response time in the medium range is not that great. Other device has a great response time is like infrared transducer, infrared thermal transducer. Okay, infrared based on the uh, infrared radiation intensity, the wavelength. So the device that measure the irradiation of the infrared. So it depend on the uh, speed of light, speed of the radiation. Okay, speed of the radiation, how the infrared radiation uh, travel, so quite close to a common three times 10 to the power of 8 millisecond per meter per second. So it's quite fast. But but for uh, point measurement, or mean the direct transducer, so mean that the transducer that we have to have a direct contact to the object of the environment that we have to measure. The response time is not that great. So, like for example, RTD, okay, so the response time is between 0.5 to 5 seconds. So what does it mean? So the precaution we have to consider when we want to use an RTD, such device as RTD. When we do the measurement, when we start the measurement, we cannot immediately take. I mean, write down, or we consider the output as the actual output. Okay, the current output as the actual output. So we must give the RTD some time. Okay, so we need to let the uh, measurement to settle down or to reach its constant value. Then we can make the measurement. So the best thing is to give some time, okay, around 0.5 to 5 seconds. Okay, 5 seconds is the longest time you have to wait. Then after 5 seconds, okay, you can start making or take the measurement. I mean, take the output as the measurement. Okay, your measurement. So the slowness is due to the thermal conductivity. So the mechanism of its distribution, like I explained before. So uh, when we expose the RTD to an object or environment to the heat, so the heat will take some time to transfer from transfer into the RTD and into the especially into the element. So it will take some time. So that's why we have to give some few seconds before we can make a measurement. Okay. Then the other characteristics is like range, similar what we have discussed in thermocouple transducer. So thermocouple have different range. Okay, uh, uh, different range, especially due to the combination of alloy, okay, material, alloy wire. Okay, so similar what we have, what we are experiencing in RTD. But RTD, we don't use a combination of different metal, but we have one specific type of metal wire. Okay, and so the range also depend on the type of material or type of RTD element. Okay, of the or RTD metal element. So, for example, okay, platinum, okay, the range can be stretched, okay, between negative 100 degrees Celsius to 650 degrees Celsius. Okay, but when we considering an RTD, okay, made of nickel, so the material or the range span, okay, is is between 180 degrees Celsius to 300 degrees Celsius. Okay, so it's much smaller as compared to platinum. So, but it's all depend on the application. Okay, the situation of the in industry application. So we need to know this requirement of the application. Okay, depend on the process or sub process. What are the maximum and minimum before we can choose a suitable type of RTD. So the other characteristic that we have to consider is the dissipation factor. Okay, dissipation factor is um, due because of the RTD is basically a resistor. Okay, a resistor. Okay, so in any resistor it will dissipate power. Okay, so the power dissipation of the power, okay, can be calculated from IR square multiplied by the resistance value of the RTD. Okay, and due to this power dissipation, the RTD will self-generate its own heat. Okay, self-generate heat. Okay, so it will produce its own heat. Okay. So we need to for a precise measurement. If we want to have a very precise measurement, we have to take into consideration this dissipation constant. Okay, but usually in most cases we don't consider. Maybe in the case of where the resolution in the application where you want to see the resolution, the small resolution or the small change of the temperature. Okay, when your application considering a very small change of the temperature. Okay, so you need to consider the dissipation constant. But in practical application, we don't consider or we don't take into account the dissipation factor or dissipation constant. So these are the okay the difference between uh, different type of metal element RTD. Uh, so we can show this is the comparison between the R over R or the change of resistance over the reference resistance R over RO. R is the resistance change. Okay. RO is the reference, yeah, the resistance change. Okay, and and this is the temperature difference. Okay, temperature difference. Okay, delta T. Okay. So as we can see in general, the RTD is linear in general. So we can see overall. So overall is linear, linear, whereas the R over RO is increasing when the temperature difference is increasing. But as we can see from this four material, or four type of uh, RTD metal element, okay. So tungsten has the best linear relationship. So it's linear. So the output is linear, but the sensitivity is low. So linear, this is a good linear. You can say the best linear. In terms of the linearity, this is the best. But in terms of the sensitivity, is the lowest. Okay, it's lowest. Platinum and copper is in the middle range. Okay, middle range. You can see platinum also among the best. Okay, linearity, okay, among the best, and sensitivity is okay, in the middle range. In the middle range. Okay. Uh, but for copper, so there's non-linearity start to appear, okay, especially after around 600 degrees Celsius. Okay, after around temperature difference of 600 degrees Celsius. Okay. So we have to be very careful if your application is above 600 degrees Celsius. So you have to better not to choose a copper, okay, copper element. Platinum, okay, it's good, okay, but here is the linear sensitivity is modest. Okay. Nickel has the highest sensitivity, but poor linearity. It's very poor linearity, so your output is not highly linear. Okay, so it has the highest sensitivity. For example, if we okay the temperature change, temperature difference is 400 degrees Celsius. Okay, sorry. Okay. If the temperature change is around okay, like 400 degrees Celsius. So tungsten, okay, the output of tungsten around 200, okay, but okay, but nickel, okay, the output is when 400 degrees Celsius, the output is uh, it's around 5, okay, it's around 5.4. We can be around 5.4. Okay, 5.4. So, but nickel have a very poor linearity. So, in my previous slide, is correct that nickel has a higher sensitivity as compared to platinum. Okay, but its linearity is very poor. So, if you choose to, if you consider nickel, so in any application where the temperature change is less than 400 degrees Celsius, so okay, if you want to go for nickel, okay, especially when the temperature is not that high, the temperature change is not that high, for example, around 200 or 300, so go for nickel. But platinum can be a uh, universal device or the element that can be considered as a RTD is the best option that you can consider. Only drawback is the uh, cost. Cost can be a bit expensive. Okay, so signal conditioning. One of the common way to apply an RTD is using voltage divider circuit. Okay, that is a straightforward way how to use RTD. Okay. But usually, because of the very small change, okay, uh, the change of the result is small, around 0.4%. That's 0.4% calculated to the output and the resistance change over the reference, okay, the reference resistance multiply 100. So usually uh, we can generally we can use a bridge circuit. Okay. This is the sample, okay, of a bridge circuit. They're like a common Western bridge. Okay, we have four arms. The R1, R2, R3. So R1, R2, and R3 are fixed, okay, fixed resistors. So and then we give a power supply, okay, power supply, and one of our arms is the RTD. Okay, RTD. So when and this is exposed to heat, okay, delta T. So RTD, okay, R, okay, we also change. Okay, the RTD resistance will also increase. Okay, so as you can see in the middle here, in this configuration, instead of having a common, okay, like a wisdom bridge, okay, common wisdom bridge, so we use a galvanometer. Okay, galvanometer. So galvanometer basically has its internal resistance, right? Okay, remember the internal resistance. Okay, and when the bridge is balanced, there is no current flowing, okay, through the galvanometer. Okay, okay, that's in a common wisdom bridge. Okay. common resistance bridge. But when we use a different amplifier, different differential amplifier, op basically different amplifier is op amp, specialized op amp used for instrumentation. Okay, okay. Okay, so this amplifier, positive, negative. Okay, so ideally an amplifier has, if you remember, it has virtually has a infinity a high input impedance. High input impedance. Okay, then what does it mean by high input impedance? So the differential amplifier does not draw any current, okay, whereas the I plus will virtually equal to zero and I negative will virtually equal to 0 ampere. 0 ampere. Okay. So what I'm trying to say here is that by using a different amplifier, okay, so this, okay, the the differential amplifier, okay, maintain the balance condition if we use a galvanometer. A galvanometer, okay, okay, a galvanometer depends on the ratio of the resistance. Okay, but if we use a different amplifier, okay, uh, even if the RTD value is changed, okay, value is changed, okay, so the balance condition of the circuit will always be maintained, okay, at any condition, virtually at any condition. Okay, because the differential amplifier does not take any current. Okay, meaning the current maintained at zero. Okay, and so, okay, by using a differential amplifier, at any point, at any change of resistance due to the exposed heat, okay, we can always use the balance equation. Okay, the Wilson balance equation. Okay, meaning that at any condition, okay, at any condition R1 over R3 equivalent to R2 over RTD. This will always be true. Okay, this will always be true. Remember, if a common is a normal Western bridge, okay, if RTD is slightly changed, though the bridge will not be balanced. So when the bridge is not balanced, to calculate the voltage output, okay, we need to use the Thevenin analysis. Okay, Thevenin analysis. Okay, if I'm not mistaken, I have shown you one example of unbalanced Western bridge. I think that is in chapter 2A. Okay, if I'm not mistaken. But okay, so in this is the how we look into the our working principle of the uh, signal condition of the RTD circuit. Okay. Okay, so this is a very other than using this signal conditioning circuit for an RTD. So if you go for this steady conditioning, of course you must have a power supply, um, few fixed resistors and a differential amplifier. Okay, uh, and straightforward way how to use an RTD and to get the EMF output. Okay, P. So because in electronic measurement, we want to measure the voltage or current, okay, of the transducer. So the common way how to configure is by using this voltage divider circuit. Okay, voltage divider circuit. Okay. In this example, as you can see, in simple circuit, okay, we have this characteristic of the RTD. The reference resistance, okay, is 50 ohm at 10 degrees Celsius. Okay. So this is the value is R10, or the resistance at 10 degrees Celsius, 10 degree 10 degrees Celsius. Okay, is equivalent to 50 ohm. Okay, and the alpha, or the constant, is 0.04. Okay. So a simple circuit as shown in this figure used to study the principle of RTD to calculate the voltage output. Okay. Uh, so we use this equation. Okay. So we know R, the reference temperature. We know the alpha, and also this is the temperature change. Temperature change means that the current temperature minus the reference temperature. So the current temperature is 200, and then the reference is 10 degrees Celsius. So delta T is equivalent to 200 minus 10. So you get 190 degrees Celsius. Okay. So to calculate the resistance, so R T is equivalent to RTO 1 plus alpha multiplied with delta T. So you get 51 plus 0.004, 200 minus 10. So 51 plus 0.004 multiplied with 190. Okay. So let's do this together. That should get 190 multiplied with 0.004, that's 1 multiplied with 50. So you should get 88. Oh, okay. So this is a voltage divider. Okay, so V is equal to 25 multiplied with RTD, okay, over the sum of resistance of the circuit, because the RTD is connected in series. RTD plus 20 plus 30. So 25 multiplied with 88 over 100, I don't know, 100. So 50, 50 plus 138. Is it? So you should get 25 multiplied with 88 divided by 15. 15.8. Alright. Anyway, so that should be the answer. The output voltage should be 15.8 volts. Okay, so we move on into the next temperature measuring device. So now here we have a thermistor. Okay, thermistor is basically a, a thermal sensitive resistor. Okay, similar to RTD where the resistors it change. Okay, the resistance change with the temperature change. Okay, but instead of using a metal wire like an RTD, so a thermistor is manufactured from semiconductor material. Okay, the metal oxide semiconductor. Okay, uh, which is encapsulated in glass or epoxy beads. Okay, so the thermistor, the biggest advantage of a thermistor, they can made into a very small size. Okay, so thermistor is the common temperature measuring device on, for example, on a electronic devices. Okay, the it is embedded in your computer or PC, also embedded in your smartphone. Uh, so they can made into it look like a common semiconductor device like a transistor or resistor, some small surface mount device. But thermistor is specifically designed from metal oxide semiconductor. Okay? So there are two types of uh, thermistor. Okay, it is categorized into the characteristic. Okay, one is called as the negative coefficient, and the second one is called as the positive coefficient. Okay, what does it mean by negative coefficient? Negative coefficient is the resistance, the resistance for NTC decrease logarithmic. Okay, decrease when the temperature is increasing. Okay. So the scale of the temperature change is in log. Okay. Basically, it's not linear. The scale is in log. But for a PTC, a positive coefficient, okay, the resistance increase uh, logarithmic with the temperature change. Okay. Uh, so you can see the scale is in log. Okay. So what we can observe here is that a thermistor has quite a huge sensitivity, very large. Okay. So very large sensitivity. So due to this large sensitivity, a thermistor can suitably be used in application where you want to measure the small change of temperature, small change. Okay? Like for example, in the biology process, where they want to study the effect of very small temperature change to, for example, to biological bacteria growth or virus growth. So they want to see that. Okay, they want to see that how they can measure the temperature change, and then they want to see the reaction. So an NTC is a device that is very suitable to be used. Okay. So this has a lot. It has a large sensitivity. Okay, but a bit drawback when using this thermistor is that the response is not linear. Okay, not linear. Where we have to before we can interpret to interpret the output, we have to find the relationship, the log and the relationship of the temperature to the to temperature change. Okay, because if you uh, to calculate the temperature output, then you need to find the relationship between the uh, resistance to the temperature change. Okay, so the equation could be in log, log equation in log scale. So the characteristic, is very extremely responsive to change in temperature. Like I said, this is very sensitive to temperature change. Okay, because it have a very huge sensitivity, okay, and so it can be used to measure very small temperature change. Okay, and nonlinear behavior. Okay, so you can see the output is in log. Okay, so it's exponentially increase or is exponentially decrease. Okay, if NTC, the resistance is exponentially decrease when the temperature is increasing. But for a PTC, the resistance is increasing, is exponentially increasing when the temperature is increasing. Okay, and other advantage of using a thermistor is have a fast response time, a faster response time due to its the construction. Okay, it does not require the the the, the, the active element is the metal oxide itself. Okay, so it does not require the transfer of heat to a metal as compared to RTD. Okay, and also it is very small. It's quite relatively small. It's small means that uh, the because heat distribution also depend on the total surface area. So a thermistor have small surface area, small surface area. It's a small effective uh, surface area. So the the measurement is relatively faster as compared to RTD. So RTD the size is much larger. Okay, so this is also the comparison. This is our comparison of the thermistor to RTD. Okay, so as you can see, an RTD, uh, so a thermistor, so the relationship to the temperature change is exponential, huge. Okay, this is the comparison between NTC, so NTC thermistor negative to NTC transmitter to a platinum RTD. As you can see, so the resistance change is quite huge. Okay, resistance change is quite huge. Okay, resistance change range is quite huge, okay, as compared to an RTD. Okay, of course, the temperature span of RTD is between negative 200 to 400 degrees Celsius. It can be used for high temperature measurement. For a thermistor, okay, it is not as robust as temperature if you want uh, to look into the temperature range. Okay, so temperature range is quite low, where here is just around 220 to uh, I think this is around negative 80 degrees Celsius. Okay, but you can see the resistance change. The resistance range, okay, is huge. Okay, huge. It's between 10 to what, 1 million ohm. So it's quite the ratio is quite huge. Okay, so that's why the thermistor is good. If you want to use, okay, in application where you want to measure the small change of temperature, okay, where you want to observe what is the effect of small change temperature. So better use a thermistor. Okay, so we finish discussing about temperature. So temperature is one of the common parameter measured in the industry. Next, we want to move on into position or displacement transducer. Uh, so position is also important in the industry. Okay, where in the industry they will be involve a lot of movement or material displacement or object displacement. So in many applications, we want to exactly know the position of an object. For example, in the conveyor belt, in the production, so in the automation process, so you want to know the position of material on the conveyor belt. So you want to know whether the material has passed a certain point on the conveyor belt. Then you want to do a certain task after that. For example, you want to, okay, sort. You want to sort the material. Okay, you want to know where the position of the material, and you want to sort the material to a certain other lines, for example. And also for example, in the robotic arm, robotic arm have many degree of freedom. It means that they have many axes. Okay, the robotic like our arm, so we have our points, joint. See, joint basically where we have a many we can turn our arm at a certain joint. For example, on the shoulder, on the elbow, on the wrist, okay, and also the fingers. So they have the rotation. So they have the so in the robotic application, so when the robot arm move, we want to know the position, or we want to know the angle movement of the arm. Okay, so that we can coordinate the process. Okay, so for example, you have two robotic arm moving from one point to another point. So before one, the the other robot can move, so you need to know the position of the other robotic arms. So that you can coordinate the process safely. Okay, so there are other application we will look into later in the class. So even your mouse, so it's basically a displacement measuring device. Okay. So you have during my time we have a ball in the middle. Okay, a rubber ball in the middle of the uh, underneath the mouse, where it is directly contact a rotary, okay, rotary resistor. Okay. So it measure the movement of the mouse on the x and y axis. Okay. But now the mouse has evolved. So basically the displacement is measured by using in, I think it's a optical. So based on the reflection of the light. Okay, so the transducer measure the displacement based on the reflection of the light. So that's another example of dispersion or position measuring device. So there are basically three common type of displacement measuring transducer. The first one is the we have the very resistive type, okay, where the movement or displacement uh, is in relationship with the change of resistance of the device. Then we have capacitance. Okay, the displacement is in relationship with the capacitance, and also the other one we have inductive. Okay. So so this okay. So these are the type of displacement transducer that is common. So we will look into it one by one. Uh, so this is an example, okay, of displacement transducer. So here we have a resistive linear position transducer, okay, where it measure the displacement, okay, of an object, okay, at certain axis now, depending on the orientation. So if we want to measure the x-axis, so it measure the displacement on the x-axis. So if we put it vertically, so it basically measure this displacement in the y-axis. Okay. Uh, so a linear transducer, okay, basically move either left, right, or top, bottom, and it depends on the position, the position of the core, okay, and then the position basically determine the total of resistance of the device. So we will look into that later. But again, these three type of distributed transducer is a passive, okay, passive transducer where it does not generate its own EMF or voltage output. So what does it mean? We have to apply a power source. We need to apply a power source, and then we can measure the output. Okay, the output, the output voltage. Okay, so the displacement is in relationship. Okay, the displacement, the the displacement is in relationship with the resistance. Okay, basically in relationship with resistance, but the output, the voltage output is indirectly proportional, okay, to the displacement. Okay, so we need to apply a power voltage to the device. So it is non, it is a non self generating uh, device. Okay, so before we go into the principle of the displacement transducer, a few things that we need to know is the difference between displacement and distance. Okay, so distance is referring on how much ground or distance or how much point of difference, an object or, or, or subject has covered during its motion. Okay? Whereas the displacement refer to how far out a place an object is. Okay, it is the object's overall change in position. Okay, so so you can say uh, the displacement has a vector. Displacement has a vector. Okay, but distance is just a scalar. Scale. When the distance has no, don't care about the direction. You want to know, okay, how far. But displacement, okay, you want to know, you you want to know the direction. Okay, for example, you travel from here, from JB to KL. You want to know uh, where you have to head, where you have to go. Uh, you need to go to south or you need to go to north. Okay. So displacement has a vector. For example, okay, so a man walk 4 meter east in this example, 2 meter far west, finally 2 meter north. During the process, so the distance is 12 meter. Okay, 12 meter. But if in terms of displacement, okay, displacement, uh, even though the subject has walked some distance, okay, in total of 12 meter, but he stopped where he started. Okay, so the subject stopped where he started. So we can say in the end of the process, okay, if we take it the displacement, okay, the subject is actually relatively doesn't move at all. Okay. So we can say at the end of the process, this displacement is zero. So that is the difference between displacement and distance. Okay, so resistive transducer. So where you can find, so basically is it the displacement is in relationship with the resistance change. Okay, resistance change of the sensing element of the device. Okay, basically the portion, okay, of change. So the device have a total resistance. So the portion of change will be proportional to the displacement. So these are the same sample of different type of resistance transducer. Okay, we have a rotary type, a common one rotary type. You have done some experiment. Okay, rotary. Okay, they come in a small size rotary. Okay, okay. Where you want the displacement. Okay, basically you want to know the, okay, rotary angle change. You want to know the angle change. Okay. And also there are linear. Okay, what we can find usually in an audio mixer device. The audio mixer device. So it has a linear uh, variable resistor, okay, where it move up and down. So basically, you adjust the displacement. Okay, that some of the lean, I mean, there could be many linear transducer, linear resistor. So each um, adjust the intensity of the audio quality at certain frequency, for example. Okay, so basically you want to make to increase or decrease. Basically, you want to adjust the displacement. What is happening? Basically, you adjust the displacement on the y-axis. Okay, or the high, low. Okay, so we here uh, as an example. Okay, uh, displacement transducer. Okay, where it measure the uh, movement or linear displacement at the x-axis. Okay, x-axis. Uh, in this case is the whether it move 3 inch Okay, finish maximum to the left or to the right. Okay, depending on the reference point. Okay, so the total or the maximum uh, displacement is 3 inch. Okay. So as you can see, this is the construction of the device where it has a wire a wound A and B. Okay. So and then in the middle of the core is the shaft, and this shaft at the tip of the shaft inside is a wiper. So this wiper is basically uh, making a contact, okay, between the wound, the winding here, winding winding of B and A to the conducting strip. Okay. So what happened? So when this wiper is moved the left to the right, let's say it's to the middle. So then when you move it into the middle, so the total effective winding, okay, in between A and B is effectively divided by two. Okay, divided by two. So remember that each wound has its own resistance. Okay, okay, so each has own resistance. So if we put in the middle, so meaning that the effective resistance between the point A and W and B and W is effectively divided by 2. Okay, but if you move to the left, for example, so sorry, to the right, so there will be less number of wind wound or winding between A and W. So mean that there will be less effective resistance between A and W, but there will be more winding, okay, more effective winding between point B and W. So there will be more resistance to between B and W, as you can represent by this figure in B. Okay, uh, this is the construction of the transducer, physical construction. So this is basically there's a contact here. There's a contact. Okay, but the contact is like a smooth contact. A smooth contact. Okay. Um, so the wiper can be moved, can be slide left and right. So to avoid the shaft from getting out, so there is a stopper here, stopper stop the shaft from uh, pull out from the uh, pull out from the transducer. Okay, so the total resistance is 5 kilo ohm, meaning that the total resistance due to the winding here, the winding here, okay, winding. So the total winding can give a effective resistance of 5 kilo ohm. Okay, 5 kilo ohm. Okay, and the applied voltage is 5 volts. Okay, so if the wiper is 0.9 inch from B, 0.9 inch from B, so the total stretch is 3 inch. Okay, so the stroke is 3 inch. So the wiper can move 3 inch maximum. But if let's say the wiper is 0.9 inch, okay, 0.9 inch from B. Okay, here, the wiper here is, let's say, is 0.9 inch. Okay, 0.9 inch. So calculate the output voltage. Okay, so we know that so 3 inch, okay, is proportional to total of 5 kilo ohm. So that's why we will need to know what is the effective resistance when the wiper is at 3 inch. Okay, what is okay? Then when we find that they are in the, let's say, RW, what is the RW at 0.9 inch, then okay, we can use we can calculate the V out, V out. So we know this looks like a voltage divider. For that, we need to know what is the RWB. Okay, so 3 inch is the total resistance. So technically, the resistance RAB. Okay, so to find V out, so we need to know RWB. What is the value divided by the total resistance multiply with our VT. So the answer, okay, given there, okay, RWB, which is the R2, is around 1.5 kilo ohm. So V out, okay, so we calculate R2 over RT multiply with VT, so we get 1.5 volt. Okay, so that is the resistance transducer. Okay, next we have uh, a displacement transducer called as capacitive transducer. Okay, capacitive transducer. This transducer, okay, the basic principle is uh, can be described by a common capacitor. So the common capacitor, the capacitance of the common capacitor is proportional to the effective area and also proportional to the type of dielectric constant. Okay, dielectric constant. So and also inversely proportional to the distance between the plate. So these are the three variables affecting the capacitance value of the uh, displacement transducer based on the capacitance or capacitive transducer. Okay. So for example, uh, we can see here below there are three configurations to change the capacitor. Okay. For example, in this on the bottom left, okay, bottom left, uh, so you can see uh, the capacitor change with the change in plate overlap. Okay, meaning that the displacement. So one the one. So we can say we have this. Let's say this is the capacitor basically made of two plates. Okay, two plates placed at the distance. Okay, at the distance, and we will apply voltage. Is so due to the static current, which is the static current, the capacitance is proportional to the total effective area of the between the plate, the dielectric constant, and also to the distance between the plate. So in this first case, the positive plate at the top here is we connect, okay, or we uh, join it to the object that we want to measure the displacement. Okay. At the bottom we have two set of negative plate. So when the plate, the top plate is moving, okay, so the effective area, the total area will be, uh, will vary, okay, will be changed. So in this first case, the total capacitance, okay, is proportional to the effective surface area. Okay. And this uh, configuration where the plate is connected to the object, okay, vertically, So where the movement or displacement of the object cause the change to the distance between the plate. Okay, so D. Okay. So when the object move further away, it means that when the object causing the plate to stretch away, to the place to stretch away, so will cause the C to decrease. Okay, so the total effective area to decrease. Okay. And the third uh, uh, example is where the object is connected to the uh, uh, dielectric material, okay, dielectric or the insulator in between the plate. So the insulator, okay, can be made of Teflon. The Teflon is some kind of polymer. The polymer looks like a plastic, for example. So it's a good dielectric material. So solid dielectric material. So when the Teflon or when the core or the dielectric material move left to the right, so it will change the total effective capacitance of the capacitive transducer. So it will be the displacement will be proportional, okay, to the capacitance value of the capacitive transducer. Okay. For example, we can see here, okay, in figure 1b, this is the common uh, on the A shows a common capacitor, okay, where one plate is will give a positive potential, one plate will give a negative potential. Okay, so the effective capacitance is zero not zero epsilon not. Epsilon is the electric constant value multiplied with the total effective area between the plate and divide by the distance between the plate. Okay. So in the complete B, in 1B, okay, when the distance, let's say the top, okay, the top plate is connected to the object. So meaning that it will create a displacement of x in the vertical axis. So there will be an increase of displacement x. So there will be an addition to the distance between the plate. So in the figure 1b, the effective capacitance, okay, when the plate move, okay, from the origin, okay, so from the origin, okay, causing a displacement of x. This is the origin. Okay, so the capacitance, okay, from, let's say this is C1, okay, change to C2. So here we can see that due to the increase of displacement, so C1, okay, will be more than C2, or meaning that C2 capacitance value will be less, okay, less. Okay. So the relationship is that C and the displacement, okay, they will be inversely proportional lah. Okay. And figure 1C, okay, 1C, okay, this in 1C, this is causing the total overlap or the surface area, the effective uh, area between the plate. Okay, remember the plate, okay, we have plate B, okay, our plate have a dimension. Okay, our plate have a dimension. Okay, so A is the original dimension. Okay. So when the upper plate, okay, displace to the left, okay, meaning there is a displacement on the vertical horizontal axis. Okay, so uh, there will be a change of effective surface area between the plate. So the effective surface area, okay, can be calculated by Wx. W is the width of the plate, x is the displacement. Okay, so this is a change, fine. So change of the change of the, so similar here. Okay, due to the change of, okay, causing the capacitance to decrease. Okay, here we can see so C A, okay, causing, okay, the change of, okay, figure 1D. Okay, figure 1D, what we have here. Okay, what we have here, the in B and C we consider the dielectric property will to be air, or epsilon is equivalent to 1, or the dielectric constant equivalent to 1. Okay. But in this case D, okay, so we have different dielectric material. It's called epsilon 2. Okay, epsilon 2. Uh, and then we have here is a gap. This is an empty gap, okay, epsilon 1, or air, okay, due to the air, epsilon 1. Okay. So here we can see the electric material is connected to the object, or measuring the displacement. So let's say in this case there is a displacement of x. Okay, displacement of x. Okay. So as you can see, the total effective capacitance between in D between in the for the capacitor. So if we simplify, so there will be two parallel capacitor here actually, effective C1 and C2. Okay, parallel, okay, C1. So C1 here is C1 in this case is given by this formula. Okay, where epsilon 1 is the constant, the constant of the material, or here, and C2 is the here. And remember for capacitor, so if we have two capacitor in parallel, okay, so the effective C total for parallel capacitor will be C1 plus C2. Okay, C1 plus C2. Okay, C1 is plus C2. So you can work out the uh, total equation. Okay, so the total equation of the capacitance when there is a displacement in D is given by this formula. Okay. Okay, so let's see this example. An diaphragm has a plate area of, okay, distance is area is 5 times 10 to the power of negative 3 meter square. Okay. And the distance between the plate is 1 times 10 to the power of 3 negative 3 meter. Calculate its capacitance if we measure air pressure. Air pressure. Okay, let's say we have plates. Okay, plates. Something like the plates. Okay. So the distance between the plate is 1 times 10 to the power of negative 3 meter. Okay, and the A effective area, or the overlap, overlap uh, between the plate, effective overlapping of between the plate is 5 times 10 to the power of negative 3 square, and that relate constant, or I think constant epsilon is relatively 1. So calculate the capacitance, we use this formula, okay, and this is the constant, okay, epsilon naught. Epsilon naught is this constant epsilon naught. So we get the total effective capacitance is around 44.25 picofarads. Okay. So this is the other uh, example. Okay. So a parallel plate capacitance type has the following specification. The area is, okay, 30 centimeter square. Okay. Distance is in 0.5 mm. The dielectric constant of the material K, okay, K, or we can say epsilon. Epsilon. Sometimes it's write as epsilon, or sometimes write as K. And the vacuum permittivity is given, constant is given by this formula. Okay. So draw and label the design of the sensor for this one measurement of the area of the metal plate change according to the displacement based on the given specification. Okay, the specification, okay, so we just sketch. Okay, not really sure what is the point where the hmm, is something is missing. Whether this is used to measure the distance. Okay, so here you can see there is a core, or the insulator, or the dielectric material, okay, is ceramic type or core, okay, ceramic type, or solid core. So we can conclude that we can conclude that this is the type of displacement, okay, transducer, for the capacitive transducer, okay, meaning that, hey, if you draw, you can draw too deep, it's okay. Okay, so there's a there's a middle, so that is displacement x. Okay. Basically, that's roughly the answer for one, but we have to complete properly. We have to label. Okay, label means that where is the value of the value of the constant here, epsilon. Okay, what's the value, and then the effective area. Okay, A, what's the A, and also the distance here. Okay, the distance is 0.5 mm. So we can see the relationship when the, okay, when the distance is, okay, change, okay, the total capacitance also will change. Okay, x c, so it will decrease lah. So if x is 0, because the capacitance is the maximum, okay, but when the core of the dielectric uh, component, or the insulator, move to the left or to the right, it will reduce. Okay, that the effective capacitance and then the capacitance will decrease. What is the capacity value if the distance between the plate is increased? Okay, distance. But in this case, what will happen if the distance is increased? Okay, so there will be a gap here. Gap, there will be gap 1 mm. So how do we tackle in this case? The third case, is slightly different. So what happened? The total effective will be here. So this is C1. C1 due to the K, okay, K material, and C2 due to the air gap here, okay, due to the air gap. Okay, so I leave it to you. You calculate what is the effective value of C1 and what is the effective value of C2. Okay, the effective value of C2. Then, of course, the C total, because this is a two series capacitor, right? So the two series capacitance, so the effective capacitance will be C1 multiplied with C2 over C1 plus C2. Okay, okay. So try to remember the principle of series, the total capacitance of a series capacitor. Okay, so I I give you some hints how to tackle this question. So this is should be how to tackle this question. Okay. So I think I stop our class here. We will continue our class next week. Okay. Thank you everyone. Assalamualaikum warahmatullahi wabarakatuh.